Robert Haynes from the National Weather Service in Burlington, and this is a recording of the Virtual Spotter training that was offered on March 24th. You'll see that each of the slides have a number attached to them. That way, if you have any questions, you can refer to that slide and email me at robert.d.haynes at noaa.gov for any questions that you might have. So with that, let us begin. So here's what we're going to talk about. What is Skywarn? Who is a spotter? And how do our spotters help the National Weather Service? We'll give you a quick overview of the National Weather Service in Burlington, and then from there, we'll get into the meat of the discussion, the different types of thunderstorms and the different flavors that you might experience of winter weather, along with some of the hazards that you might experience with them. And then we'll discuss a little bit about Lake Champlain forecasting. So Skywarn is a program that was developed and really became integrated in the 1960s. It's made up of a national network of volunteers who report and are trained by the National Weather Service. They provide us a valuable resource in that, given all of our fancy radar, satellite, other observing technologies that we have, the Skywarn Spotter is the only one that's able to give us ground truth. These volunteers provide us a wide range of reports ranging from significant wind damage, whether or not there are trees or power lines down, or give us hail measurement, or give us intense snowfall reports. And also they can give us reports of a lack of any of those items. Anyone could be a Skywarn spotter. It ranges from emergency managers to local law enforcement to even students and members of the general public. Anyone is welcome to join the Skywarn Spotter program. We do ask that if anyone is younger than 16, we ask at least for your parents' permission, given that these storms can be a little on the dangerous side. Again, how to become a spotter. This is a voluntary network. It's something that's completely free. You can engage in it as much as you want or as little as you want. We only ask that you're trained by a forecaster from the National Weather Service through any of the following means, whether that be in person or through a virtual course like this one, or through the Comet NetEd course that you can find online in the link attached. If you do happen to move from our location, feel free to contact that region's National Weather Service, and they can help you get moved to that region into their spotter network. Each different National Weather Service is going to have their own setup for their spotter program. Upon completion of the course, if you would like to become a spotter, we ask for your physical location and a contact number that you will commonly use. This will be helpful for us to quickly and accurately input information. And it does happen to be that if we do see a storm in your area, we may be giving you that call. Again, let's bring up why we need spotters. Our radar, as great as it does have its limitations. We have many mountain ranges that block our radar signature, and oftentimes the radar is going to see what's up in the clouds, but not necessarily what's happening on the ground. You provide us with that knowledge of what's happening on the ground, which helps us prepare a better message for general public response. It gives us credibility to our warning. A spotter can be a source cited in our warning products, and that helps improve our accuracy and our general knowledge of which storms we issue verify or which ones we may have missed. It helps us to ultimately protect life and property. So radar is going to see all of what's up in the clouds, but the spotter is going to be the individual who's going to see that wall cloud that might be prepared to produce a tornado. From your report, we can then locate where you're at and then assign a severe thunderstorm warning or a tornado warning to that storm that you're spotting. This goes a long way in protecting life and property. We rely on our spotters and we rely on reports for washed out roadways in a flash flood, or when a thunderstorm is producing downburst conditions across the lake, or when a tornado manages to sweep away an entire theater. Let's talk a little bit about the organizational structure of the National Weather Service. The National Weather Service headquarters is in Silver Spring, Maryland, and they are over a variety of regions. These regions are different segments over the United States that are responsible for different field offices. There are also several national centers like the Storm Prediction Center, which you will likely interact with the most as a spotter, that produces probabilistic outlooks of different severe weather hazards, whether that be for damaging wind, hail, or tornadoes. You might also engage with the National Hurricane Center in Miami. They produce a lot of the tropical cyclone reports and discussions and give you all of that cone of uncertainty information. And then there's also the river forecast centers. In the National Weather Service in Burlington, us in Vermont, we are located within Eastern Region, and our river forecast center is in Taunton, Massachusetts. These are different offices that we might interact with on a larger scale just to discuss some of the things that are impacting us before the region, and then they will represent us to all of these different national centers. Our area of responsibility is the National Weather Service in Burlington. We cover the 4 northernmost counties of New York, as well as much of Vermont, excepting Bennington and Windham County. You'll see in the topographic map, we have quite a bit of terrain in our region, ranging from the St. Lawrence River Valley to the Adirondacks, to Lake Champlain in this middle there, and then the Green Mountains of Vermont. And then the far extremes, we have the Passumpsic and Connecticut River Valleys. Kind of mapping out some of these different regions. Each of these different regions is going to experience different types of weather and climate just as a result of the wide variety of terrains that we have here. They play a big role in what we do, and this is just a quick overview of some of the different regions that we might refer to here at the National Weather Service in Burlington. At this point, we did have an audience member ask a question about where each of the different forecast zones are to help you find where that is. If you do look at weather.gov/BTV and use our point and click map, you'll scroll down to the bottom where you see additional forecast and information. If you click that area that says zone area forecast for Western Chittenden County in this case, it will open up that zone and you can see it there highlighted on the map. If you want to know what zone you're in, that's an easy way to figure that out, which can be a useful tool when you're a listener for NOAA Weather Radio that can let you know what area you might want to pull. Before we head into any discussion of the storms, let's talk first about safety. When it comes to these type of thunderstorms, having good situational awareness is key, and having all kinds of communication outlets is also important. It's important for people to know where you are, what you're doing, to make sure that they can check in on you and know that you're safe. But it's also important to be able to have a plan in place if weather gets bad that you can escape to and find a safe zone. Your safety is always number one. We never want you to go out of your way or put yourself in danger to report storm information to us. Severe thunderstorms take the lives of about 280 people every year. Your best plan of action is just going to be to go inside. When thunder roars, go indoors. Or when you see floodwaters, turn around, don't drown. Oftentimes, your safest place is a sturdy interior structure. Flash flooding will be the #1 threat that you often see here. Practice good safety. Make sure you never go towards running water. Seek higher ground if you do encounter floodwaters. It only takes 6 inches of fast-moving water to knock over a person, about a foot of fast-moving water to carry away a small car, and 2 feet of water can carry larger trucks and SUVs downstream. Now let's talk a little bit about the different types of severe weather we have listed in order of organization from top to bottom. Single cell thunderstorms will be your least organized, followed by multi-cell thunderstorms, squall lines or quasi-linear convective systems, supercells, and most organized at the list is our tropical cyclones. The single cell thunderstorm has a fairly short lifespan. It's going to consist of an updraft that grows. That typically happens in a 0 to 15 minute time frame. That can be generally what's going to happen is they do not move a whole lot, so you get no separation of the updraft or the downdraft. And so once it reaches maturity, when your severe weather is most likely to occur, you have equal parts updraft and downdraft. Those downdrafts can be where your damaging winds and your heavy rain comes from. And once your storm becomes downdraft dominated, where you have no more updraft going into the storm without any vertical support, your storm is going to decay. Here's just a quick schematic. Oftentimes your single cell thunderstorm is going to develop on a hot summer day during the middle of the afternoon when good heating is allowed to these little parcels of air to lift up and then condense into water droplets. As the atmosphere becomes rain cooled, you will start to get downdrafts as your droplets head down on the surface. This is where your gust front occurs. And then at a certain point, your cold pool within your single cell thunderstorm is going to basically wipe out any opportunity for warm rising air, and your thunderstorm is over. Here is a North Country example of a single cell thunderstorm. This occurred in Chazy over in New York. Despite its relatively unassuming appearance, this little thunderstorm managed to produce a 63-mile-per-hour wind gust. So it did have the capability of producing those damaging winds despite its unimpressive appearance. So with that, a single cell thunderstorm is typically going to be typified by brief gusty winds, maybe strong or damaging. There's the potential for a brief period of hail depending on how strong that storm is. It's not common, but there is the possibility that it could produce a tornado in the right environment. The biggest threat that's going to be from your single cell thunderstorm is going to be lightning. The multi-cell storm is going to be your most common. This one is going to feature several storms in several different stages of a thunderstorm's life cycle. What can end up happening is these can congeal into different clusters. Typically, the individual cell is going to last 30 minutes, but the process that's involved with the clusters, the development and redevelopment and decay of old systems can result in at least a small measure of organization that lets them last for at least a few hours. Severe weather will still be isolated and of short duration, but it will typically be a bit more widespread, mainly because you have more thunderstorms. Here's a look at a schematic of the multi-cell thunderstorm. You'll typically have a parent cell, in this case, cell number 2, which is in the stage of its downdraft. And then you'll have other cells here that are in their stage of the updraft. The multi-cell is going to have, you'll see like a line of clouds in the distance, and this meteorologist here positioned radar with what they were seeing in real life, just to kind of give you a glimpse at what that looks like. And you'll see that they've also labeled that these storms often produce gust fronts, where there's at least a little bit of organization where multiple downdrafts are kind of lining up. New storms like to initiate near these gust fronts due to the favorable convergence that they supply. And of course, a North Country example for you. On Independence Day in 2012, a cluster of thunderstorms moved down Lake Champlain. And with that increased organization, you have features like shelf clouds that Mike Cannon has captured here in Colchester Reef. And so typically with that higher level of organization, that greater intensity, you have the higher likelihood of seeing strong damaging winds, periods of brief large hail. Isolated tornadoes also possible. But another concern with these, with multiple storms occurring, is that you could also see some flash flooding, especially in the case of any training storms. And of course, you can also experience frequent lightning. The squall line is a bit more organized than even the clusters. Sometimes even clusters of storms, of multi-cell storms, can become a squall line. Typically, a squall line will develop with a strong frontal system. They can also occur in the summer in a more extreme example known as a derecho, which is just a way to define a strong straight line wind event. These squall lines are typified by continued updrafts, and this is due to the favorable interaction of shear and convergence along the front, allowing for continual updraft interactions and for new cell development as the system is moving. These do have different levels of organization. There can be breaks within a squall line, or they can be completely solid, extending for well over 200 miles. Their duration will depend on the speed of which they're traveling. So it can be over in a matter of minutes, or if there's training cells, it could also be for hours. The derecho is the extreme example. These are more favorable in the summertime and will result from cold pool interactions with clusters of thunderstorms in the middle of the summer with a good favorable environment aloft. These can move really fast and they can catch you by surprise. The average speed of this derecho that took place in the Ohio River Valley was 75 miles per hour, and along its path, several reports of 70 miles per hour or higher gusts were measured, and it produced widespread damage as it moved south and east. These are the extremes, though, in terms of squall lines. These will typically not occur in the North Country due to the presence of our terrain features. And a quick cross-section of a thunderstorm. Typically with a cold front, you'll have a rear inflow. This is from the cool air descending behind the front, and that interacts favorably with warm air converging right ahead of the frontal line. And that typically will produce things like your shelf clouds or your rolling clouds, or features of organization that lets you know you're in for a little bit more of a serious storm. Here's a nice picture of those shelf clouds. This results as that moist, warm inflow rides over any of that colder outflow ahead of the front or just right along it. With their rolling and twisting motions, they can look like a tornado, but that's not the case here. These will also generally be more common the more organized and how well put together your squall line actually is. Here's just a quick schematic to show that. The downdraft of a thunderstorm can also aid with cold air coming into the flow of the thunderstorm, and that can create these turbulent motions that help these clouds to look like they're rolling. And of course, a North Country example in 2008 from a squall line that passed through Colchester, where you have the shelf cloud helping to separate between precipitation-free areas and areas that are now experiencing or were then experiencing very heavy rainfall. Like I mentioned earlier, clusters can organize into squall lines like this line on May 4th of 2018. Cluster of storms developed over New York, and as they moved into Vermont, became a squall line with several bowing segments. This storm system produced several damaging wind reports across the area, and that will be your greatest hazard with the squall line. It will be strong to very strong damaging winds. There is the potential for large hail as well due to the greater organization in a squall line. Embedded tornadoes are also possible, especially if there are lots of bowing segments in a line, generally along the northern edge of any bows. With a squall line, you might also have the potential for flash flooding. It will depend a little bit on whether or not you have storms training ahead and along the front, and if the frontal motion itself is slow. The area that's going to be impacted from a squall line will be a bit more widespread, given that there is a larger area of strong damaging winds occurring. The supercell thunderstorm is your most organized example of a thunderstorm. The strength of the updrafts can be quite extreme in that they exceed 150 miles per hour. The most defining characteristic of a supercell thunderstorm is going to be their rotation. 80% of your severe weather is going to be produced by a supercell thunderstorm, and 20% of tornadoes are produced by supercell thunderstorms. Generally, the thing that also defines a supercell is the fact that their rotation helps to separate their updraft from their downdraft, allowing them to have a longer lifespan, like one of the deadliest instances to occur in 1925, where a supercell tracked for 300 miles and killing about 600 people in the process, which is just a reminder that these systems can be dangerous and that it is important to have a plan in place when you encounter these type of systems. The classic supercell is defined by two different regions having a downdraft, and where a little area of inflow helps to create this little hook echo. What will happen here is the rotation into the thunderstorm, like when you have south winds at the surface but west winds aloft, helps as your updraft is taking place, it will begin to rotate, and that gives it this hook-like appearance and what might be known as a weak echo region or a bounded weak echo region in some cases. With the rear flank downdraft, you're going to see downdrafts wrapping around the storm system, and that's where you're going to see your wall cloud developing. And your tornado is going to typically happen in this little narrow area that's precipitation free, where you're getting that warm inflow contrasted with that cold downdraft air. Just like any thunderstorm or just like any area of larger low pressure systems, these systems can also occlude, and in that case, what happens is the cold rear flank downdraft will end up wrapping all the way around and cutting off the inflow into the tornado, at which point it becomes occluded and eventually dissipates. Here's a quick schematic on the general structure to show the tornado between the general area of precipitation-free zone where you have the rear flank downdraft, and where your forward flank downdraft is on the right, where you have your heaviest rain, your largest hail, and the likes. And just to give you the idea of the rotating air around that wall cloud where your tornado is most likely. Here is a pretty good North Country example, thanks to how close it was to the radar. A supercell developed near Plattsburgh. You can see that classic hook signature, and you can see a little bit of the weak echo region there near Grand Isle, where you had lighter returns, less DBZ values than you had just nearly over the town of Plattsburgh or just right over land. That's where your largest hail was likely occurring and your heaviest precipitation. And in general, the typical hazards with these, supercells are geared and most likely to produce the very large hail that's going to be greater than 2 inches in diameter. With the stronger updrafts associated with a supercell, you also have the greatest chance for extreme downburst winds in excess of 80 miles per hour. There is the possibility that there's a tornado, and it's possible that they're going to be strong as well. And as with any thunderstorm, there is always the threat of flash flooding, especially in supercells that have very warm, moist processes that aid in precipitation efficiency. Tropical cyclones lie at the end of the organizational structure of thunderstorms. These are very organized convective systems rotating around a low pressure center that's driven completely by warm rain processes. And what that results in is there are a lot of small droplets in the cloud, and that allows for very rapid gains in precipitation. You have a GIF of Hurricane Irene as it was moving up, and you can see even well before the area of low pressure reached the New Jersey coast, it was already precipitating in our region. The system size and whether or not it's moving very fast or very slow is going to dictate how much heavy rainfall is going to occur. These systems will generally produce about 3 to 7 inches of rainfall, but on the extreme end, they can produce rainfall totals in excess of 50 inches like Hurricane Harvey, and they are also capable of producing isolated tornadoes. At this point, we had a couple of excellent questions. One was related to how downdrafts work. Kind of like we mentioned, your downdraft can rotate around a supercell and cut off the inflow, but also in a squall line, if you have a downdraft that's moving too fast for the environment of shear or convergence that it's running into, it can actually cause your squall line to weaken as a result. We also had a general question about supercells and how the interactions took place with just the shelf cloud and the wall cloud. But generally, the most important thing to consider with these is that it's all about how the interacting air masses work together to produce the tornado. Let's go on to the next topic of discussion. Let's look at the Storm Prediction Center, which will be one of your best resources when it comes to looking at whether or not you have severe weather for the day. The Storm Prediction Center rates the potential for severe weather through categories ranging on a scale of 1 to 5. 1 would be a marginal or isolated case, whereas 5 would indicate widespread, long-lasting severe weather. Category 5 type levels of thunderstorm risk are not often put out by the Storm Prediction Center. It's something that they do not do lightly. I don't know if there's actually an example I can think of in the North Country that has had a high category day. But I do know a good instance of a moderate day was at least the May 4th event, perhaps. This is an example of the April 27th, 2011 outbreak that occurred in North Alabama, where several tornadoes were forecast and occurred. Even on those days, you can still get some impact in the North Country, but this is a nice example in the fact that it shows all 5 of the different categories for the day and shows the area of greatest threat. Let's discuss quickly what a watch versus a warning is. A watch is going to say that conditions are favorable and that you should be on the alert. It's like, for example, when you're baking, you have all of your ingredients. You have your flour, your sugar, your baking soda, your chocolate chips. Everything that you need to make cookies is available. A warning is when it's imminent or when your cookies are now baked. That's saying that's your time to take immediate action. That's when you need to be putting your safety plan into action. To give you a general timeline of the different products released in anticipation of a severe weather event, it'll typically start with a hazardous weather outlook from a weather forecast office like ours. Occasionally, in particularly high impact days, we might issue a spotter information statement requesting spotter activation. We'll coordinate with the Storm Prediction Center, who in anticipation of watches will issue these things called mesoscale discussions. And at that stage, we're collaborating with the Storm Prediction Center on where a watch might be issued. Once we have collaborated, we then broadcast the watch. You'll hear the alerts on NOAA Weather Radio, and that's when they become streamed to any TV broadcasts. And after that, in any watch, we likely will begin to experience severe weather. As severe weather occurs, you help provide us these local storm reports. We generally ask for roads or landmarks or streets that you're located along to help put a latitude or longitude on where any wind damage, hail, or tornadoes occurred. And that helps to create maps like this, which the Storm Prediction gathers for every day of the year to show where severe weather has occurred. And if you have any GIS inclinations, you can pull much of this data off of the Storm Prediction Center and using GIS applications. To give a quick climatology on the severe weather in the National Weather Service Burlington, typically July is our most active month of the year for severe weather. Beginning generally in May is when our severe season typically starts. You'll notice a higher ratio of hail in May. Typically that's going to be a result of the cooler conditions during the month and the cooler conditions aloft, whereas in July, conditions are much warmer, and that tends to allow hail to melt before reaching the surface, and will then make the ratio of wind damage a bit higher. Severe season quickly cuts off after August. By September, severe reports are greatly declining, generally less than 200 in that 56-year span from 66-year span, excuse me, from 1950 to 2016. With a view of the map of spatial distributions for wind, you'll see that it's not really associated with any one particular spot, but generally areas that are going to have higher populations are going to report wind events more often. We'll be able to see these events occur, whether they are from reports from you. Sometimes we can spot them on radar where velocities indicate that a downburst is occurring. As downburst wind hits the surface, it has nowhere to go but out. And so as the signature of wind coming in and out of the radar, noted in green for velocities coming towards the radar and red going out, we can see these downburst winds. And if we do see them, we are probably a bit late on the warning. But if you are in that area, we might be giving you the call for whether or not you see any damage associated with these downbursts. Their appearance is going to look something like this, where they flatten trees in the environment into a bit of a pancake there. Because the winds are descending rapidly down from the thunderstorm, they're going to go out. And so you're going to have all of these trees and everything kind of diverge out of where the downburst is centralized. Looking at hail, we don't usually get too much in the way of hail here in the North Country. Typically, we don't have an unstable enough environment. We can get large hail and significant hail greater than 2 inches. In general, these are also going to be reported near population centers, and you'll see that they are also clustered around road networks in our region. Hail forms by water droplets as they ascend above the freezing level. They'll begin to freeze, and then the hail is going to begin to circulate above and below the freezing line. And that's what's going to give it the opportunity to form several different layers so that if you were cut it into a cross section like you have on the right, you'll be able to see each of the individual layers as ice is developing around your hailstone. If the hail becomes too heavy, or when it reaches the downdraft, your hail is going to descend to the surface, and that's when you're going to see those hailstones reaching the ground usually. Vermont's record hailstone was captured here in 2009 with a 3 1/4 inch diameter. We measure hail from end to end. You can also measure its circumference as well. Just to give you an idea, like hail can be a nice perfect sphere, or it can be kind of globular like this piece of hail, and that can make it particularly dangerous as it falls to the surface. We use these different common objects as measures of hail size. Typically, we like comparing them to different sports balls because they are standard regulated, going to commonly be the same size. Whereas if you had marbles are going to be all kinds of different sizes and might not be as useful to us. So this is just a quick chart for reference. On the high end of things, grapefruits and softballs, that's probably not going to happen in the North Country. We typically get somewhere in the ballpark of penny-sized hail to hen egg-sized hail. Looking at tornadoes over the last, or not the last 66 years, but just looking at this quick time frame from 1950 to 2016, you'll look at the map and you'll see that there are no EF3s or higher in the North Country. In general, they're going to be highly influenced by the terrain of our region, typically favoring the valleys, but it will depend a little bit on how the profile of the storm veers with height, and will depend a lot on the instability, which is not always available here in the North Country. So in categorizing tornadoes, tornadoes are violently rotating columns of air that are in contact with the ground. Generally, here in the North Country, we will only experience one or so every year or every other year. They aren't very commonplace. So we'll typically see weak tornadoes, but even then, most tornadoes are weak tornadoes that are EF0s or EF1s. These are the less deadly. Only 5% of tornado deaths come from these weak tornadoes. They'll typically also have a short lifespan. The damage that they incur are going to be the way that we measure the wind speed or approximate it. Typically, these are about 65 to 109 miles per hour. Stronger tornadoes, about a fifth of them is the ballpark, will be able to last a little bit longer and produce wind speeds of 110 to 167 miles per hour. On the extreme end are violent tornadoes, which cause the majority of deaths. Fortunately, these are very rare. Only about 1% of tornadoes are these dangerous EF4s or 5s. But due to the fact that they are so strong, that often means the environment that made them is favorable. They can go a very long time. They can last over an hour, go extreme distances over 50 miles, and produce wind speeds in excess of Category 5 hurricanes, and will be able to level any structured surface or structure almost. One of the good recent examples we had in the North Country was an EF1 that went through North Cambridge. The way that we do this, when we get reports of a damaging tornado, we will go out and basically interview the tornado in the sense that we'll go along its path and we'll base it off of radar, off the reports we hear, and we'll go around and take pictures, talk to the people that were impacted by the tornado, and get an idea of some of the impacts that they have. We have a nice folder for reference that helps us to estimate the tornado would be rated based on the damage that's evident. And here's just one example of that tornado that went through North Cambridge. You can see it uprooted a tree, snapped several trees as well, which is likely how it earned its EF1 rating there. And let's go into winter weather. We'll talk a bit about the common scenarios in winter. The nor'easter, terrain-driven upslope snows are very important here. Lake effect snow, Alberta Clippers, and of course, snow squalls. We'll also spend a bit of time talking about some of the best practices for measuring snow and ice. The nor'easter is going to follow a track generally from the Gulf of Mexico and along the US coast. Depending on where the low tracks will affect how much snow we receive. These storms are typically going to be on the higher end of winter weather that we experience here. Typically, the area of low pressure is going to produce strong winds. If it's in excess of 35 miles per hour or more, it drops visibilities below a mile for an extended period of time. That's what we call a blizzard. With these, we can also see impacts of blowing and drifting snow if these winds last a significant time. Now, the low track is the most important feature. We typically consider the 40, 70, or 40 north, 70 west as the benchmark for these systems. We typically want it a little further west than that, but Boston would probably favor it a little further east. Where the low track is important as it often affects our precipitation type and where the band of heaviest snow is in relation to these. Oftentimes, we'll make up the difference from upslope snow events as an area of low pressure moves into Maine or the Canadian Maritimes. Any moist air that might be near the surface is going to move from the northwest in Canada and down to the southeast, where it then interacts with either the Adirondacks, the Greens, the White Mountains. And what ends up happening is you have very localized terrain-dependent events where snow could be a trace in the valleys, but could be several feet in the mountains. And you have two examples here, one from December of 2010 and another from November of 2003 that can show you some of the extreme differences that can occur in these upslope events. You have a donut hole in the Champlain Valley, but just anywhere in the Adirondacks or in the Greens, you can see amounts measuring above a foot of snow. Another common setup is when we get lake effect snow. This requires an unfrozen lake. That's the best way for any of that water to evaporate and allow that moisture to get into the atmosphere. We typically like to see winds just a little west of south or to the southwest. That could be at anywhere between 240 and 280 degrees. We want very cold air to move over that relatively warm lake, and then that will produce some of those lake effect snow showers in our area. Terrain shadowing also plays a role here. The Champlain Valley is typically going to be terrain shadowed, and then it'll kind of pick back up as orographic lift takes hold for the greens. This is a particularly good event, one that happened recently at the end of last month, where a lake effect band persisted for nearly 36 hours and deposited feet of snow downwind Lake Ontario. And not just that, its bands extended quite a long ways, hundreds of miles all the way into Maine from Lake Ontario. And even below the one that was off of Lake Ontario, you can see another stream of lake effect snow that had set up from Lake Erie in central New York. And the Alberta Clipper, these are typically going to be more light to moderate events, but the thing that characterizes them is that they're going to be very cold. The limited moisture from a continental air mass typically will result in only 2 to 5 inches of snow, but sometimes the cold can be just as impactful with these events. With a snow squall, the big impact with them is that they produce snow showers with very heavy snow and a very short span of time, and the danger can be especially if temperatures are hovering right around 32 or 34 degrees, that they suddenly drop and then you have a resulting flash freeze. The rapid onset can catch motorists by surprise and can make snow squalls particularly dangerous, causing large pileups from an otherwise innocuous system. Generally, these are going to be caused when lake moisture is streaming ahead of a front with relatively cool air ahead of it and relatively unstable air as well. With a particularly strong front, you can get an organized band of snow, almost like a squall line in the summer, that can produce these heavy snows and strong gusty winds. It's like a blizzard in 30 minutes. It arrives and then it's gone. Let's change gears and talk about snow measurements. Typically, the best place to find is an open ground area that's unobstructed by too many trees or buildings. Ideally, you'd like to have a snow stake that can measure depth on or near your board. And so what that looks like with the official measurement, we take the measurement of the snow depth every 6 hours. We will wipe it clean and start again and add up their totals for our snowfall. You can also measure hourly rates as well, but the total snowfall for any given event will ultimately be that summation of the 6 hour total. And if you do not happen to have a snow stake on your board, it's encouraged to take multiple measurements across the board and then average them together. Generally, the benefit of having a snowboard is that you will be measuring purely what's on the board. If you're measuring in grass, you might end up actually measuring a little bit of air between the top of the grass and right down between the surface. Oftentimes, your ground is often going to be warm as well, radiating heat upwards, which can melt the bottom of your snow layer. So snowboards will just give you generally more accurate measurements of snowfall. Looking at measuring ice, you can measure either on a flat surface where ice is accreting, or you can measure on a branch. Main thing if you're measuring on tree branches or poles or any other kind of surface is to make sure that you subtract out the branch by measuring the radii on either end of the branch and just adding those measurements together instead of including the tree branch. We will now gear into forecasting winds for Lake Champlain. In terms of maritime forecasting, we issue things like lake wind advisories and lake thunderstorm advisories during the summer when most of the boating activity is going on. The main thing that dictates what your marine weather is going to look like is going to be all about mixing potential. Less friction over water allows for winds to go unobstructed by things like trees and buildings that we have on land surfaces. The thing that's going to matter the most is whether or not your water temperature is warmer or colder than the surrounding air. A cool air mass atop very warm waters is going to be unstable, and that's going to allow for winds to mix down towards the surface. And we also have in the Champlain Valley channeled flow, where winds will accelerate through the Champlain Valley between the Adirondacks of New York and the Greens of Vermont through the Bernoulli principle. As they channel through the valley, they're forced to accelerate since they are fitting within a narrower gap. Just to give you a seasonal look at when winds are going to be gustiest on the lake, winter is often going to be the time of when they are gustiest. Lake waters are going to be a little slower to warm than your air mass. And then it's also going to be a bit cooler when you go in the summer, or take a bit longer to cool in the summer. So in the winter, you'll have cool sea surface temperatures and cold air, and that means your boundary layer is going to be unstable. You'll have a lot of mixing and a lot of gustiness. In the spring, that reverses. Now your lake is cold, taking a long time to warm up, but your temperatures in the air are starting to come up already, and so you end up with a stable layer. In the summertime, your lake is still going to be relatively cool, but now your warm air is going to be very hot because it's summer. Generally, your winds are going to be stable because the boundary layer is not going to be able to mix down to the surface. However, in the instance that you have a thunderstorm, you still might experience strong winds on the lake. And then in the fall, it's going to take time for those lake waters to cool, and now your air temperatures are relatively cool, so it'll again become unstable. With a look here on the frequency of 25 knot winds or greater in Colchester Reef, we recently updated our study, and you can see the same pattern unfold with the summer on the far left with relatively stable conditions. When you get into fall and winter, you have more occurrences, and then as you head deeper into spring, your frequency of 25 knot winds begins to drop. And as a result of channel flow, when you're in Lake Champlain, your winds are typically going to be directed at either the south or the north. Due to the nature of the flow here, the mountains are going to typically prevent west or east winds from reaching Lake Champlain. And that's just due to the way that our topography works. It just makes it more favorable for winds to channel either from the north or from the south. Thanks for listening to this presentation. If you are interested in becoming a spotter, give us a call. You can call 802-862-2475 and hit the star key. That will reach any operational forecaster that's at the National Weather Service. You can also email me at robert.d.haynes@noaa.gov, or you can even email nws.er.etv.operations@noaa.gov and let us know you're interested in being a spotter. We'll ask for your name, your address, or if you're not comfortable with providing an address, you can also provide a lat lon, and then we'll also ask for your phone number in the instant that we might want to contact you. Feel free to also join us on social media on Facebook, Twitter, or YouTube. And if you are interested in becoming a spotter, feel free to use our unlisted line, which I have provided here on the bottom left. We are open 24/7. You will always find a forecaster at the end of the number that we provided. Report to us any tornadoes or funnel clouds that you might see, any hail. Heavy rain and flooding will be one of the biggest things that you see here. Also, heavy snowfall, as well as any instances of damaging winds when that knocks over any trees or power lines. We'd like to hear about it. Ultimately, we want to be able to create more content and to be able to engage more with our users. Many of us here could talk for hours about the weather and about each of the different topics that we've discussed here. We've barely scratched the surface. So we plan on doing more of these in the future. If you have any topic that you are interested in hearing about, please discuss it with us. Let us know, and perhaps we will plan our next spotter talk around your interested topics. There are many good resources that you can find to help you learn more about spotting. We encourage you to attend multiple sessions, take refreshers every 2 to 3 years to be able to learn more. And feel free to view our Skywarn Spotter page at weather.gov/btv/Skywarn. We plan on updating it in the near future to be able to hopefully engage our users more. We want you to be able to call us and email us at any time if you have any needs. With that, thanks for listening and hope you have an excellent day.